Can you hear me? Okay, well, so today we're going to speak about how you could use architecture to empower yourself to make your code more maintainable in the long run. Oops, I have this thing. Let me begin about myself. So I'm a Drupal PHP developer with almost 10 years of experience. I've been working on long-running projects, enterprise scale, that lasted for years. I've also been part of outsourced companies where you ship websites quite fastly, I don't know, once a month or so. Currently, I'm a Drupal developer at a company here in Zagreb. It's called Web Solutions Agency, so you can always find me at the office in case you need. Now speaking about the architecture, the subject of today's talk, well, I think the most concise definition of architecture is whenever you code, try to maximize the amount of objects that you do and minimize the amount of relations that you use to connect those objects. And let me explain what I mean by that. We could have had, well, a system like here. You have some kind of system, you might distinguish some possible components that there are, I don't know, there could be some billing system and user notification, for example. But the boundaries between those subsystems code, they're not strictly defined, and that's why I made it kind of fuzzy. So it mostly exists in your imagination and not so much in the code. Then some developer could have come and could have done some architectural thought, like on this other part of this slide. Then he would come up with explicit defined interfaces through which the components communicate with the main system. And then basically we're going to end up with some architectural work executed. Each component is going to be self-contained in its own box. And here's an important note that I should make, that as far as features, as far as business value, we haven't changed anything. It used to do the same thing as it does now. So architecture is not about business value or features. It's more of how do you cook the code, I say. How do you organize the code internally? So why would you care at all about architecture if it's not directly connected to business value? Imagine tomorrow your boss comes in, he requests some kind of feature. In case you haven't done the architectural work and you're staying in this line, then in order to execute the change that you requested, you actually must dig through the whole big green box. You must assure that you haven't introduced any side effects and so on. So you literally have to dig through 100% of your code base. On the contrary, if you have some components defined within your system, then actually things become easier, because first you got to define, does the change that I'm requested to do, does it belong to one of the components or to the main system? Let's, for the sake of example, suppose that it belongs to this subsystem 1. Well, that's awesome news, because you only have to dig through that small piece of the code, and you shouldn't care so much for the rest of the code base that you have. And after you've introduced the necessary change, the only thing you have to do is to verify that this interface, this red bridge, well, basically the component still implements the same interface, and you don't have to retest other parts of your software. That way, your task has become simpler, because you've only had to deal with, well, roughly speaking, 30% of your code instead of the whole thing. So that's the part about maximizing objects. There is another part about minimizing relations between them. Why would you care for minimizing relations? First of all, human brain can only hold so much of things at the moment, objects and relations between them. Another reason to keep it in mind is that in case your boss comes to you again with some kind of feature request, you analyze what he actually means, and it ends up that you actually have to change this bridge, the interface. The thing that he requests from you doesn't clearly belong to one of the components. Well, that's a relatively bad news, because if you're amplifying the interface, it means that you have to redo the component on this side of the bridge, and also you have to do some adjustments on the other part of the bridge. So that's more or less double the work. That's the idea as why you should try to minimize the relations in your system. And you might by now get the intuition that Actually, they are mutually exclusive, because normally the more objects you introduce, the more wires, the more interfaces and relations you will require to keep them all connected and aligned with each other. So that's really where it comes down to philosophical way to see it. There are no strictly defined rules or any kind of formulas, magic formulas. It's all up to your gut feeling and kind of feeling of creator, of the art person. Is it worth to introduce this new next object at the price of additional relationship that it implies? So always keep it in mind and always use your critical thinking about it. So I would say that as far as we're talking about architecture, interface is the keystone of all the things, because eventually it is interface who defines the amount of objects. Because if we split something by introducing interface between it, well, from one object we got two objects. And interface by itself, it also acts as a relation. So also, it is again interface who dictates the amount of objects and the amount of relations in your system. That's why, well, I have a dedicated slide to interface. So what I could say about interfaces, try to make an interface a complete one, and by complete I mean such an interface that fully describes the component that is going to implement that interface. So whoever else is going to use that component has basically enough of strings to pull, enough of channel, bandwidth in the channel to communicate and to express all that this system that is using our component. So it has enough, channel to say what it needs from that component. By having interfaces complete, you also actually do some nice thing. In case your interface is not complete, you might be tempted to throw some small hidden wires between components that bypass the interface. And this is not good, because you shouldn't ever do that. And if you start doing that, sooner or later, you're going to end up with, again, not a clearly architecturally defined code, but everything is going to become fuzzy again. And, well, this is not good. Another thing that I want to, while staying on the interfaces, I want to bring up is I'm definitely not speaking exclusively of object-oriented interfaces. There could be, well, the interface I'm speaking about, it could take the shape of object-oriented interface, but it's not only that. It could also be just a function that receives certain input arguments and provides certain output arguments. It could be also just a verbal agreement between the developers. Whenever you execute this kind of operation, make sure that you put it, I don't know, in some kind of locked results. That's also an interface to me. So to summarize, it's not about the shape that you put to an interface, but its content, richness, completeness of that interface, and whether everybody clearly understands and correctly uses that interface. So how could you come up with complete interfaces? I would suggest you in general to speak one level of abstraction ahead of the problem that you're trying to tackle. And here I will cite Einstein, who once said, if I had 60 minutes to solve a problem, I would spend 55 minutes thinking about this problem and 5 minutes thinking about solutions. So what would he be doing during those 55 minutes? He would probably, again, would try to abstract away from the specifics of that problem to one level of additional abstraction to understand it on a broader, deeper level, the problem that he's trying to tackle. And normally, when you think on theoretical level, you naturally come up with complete interfaces. So here I have kind of illustration, this picture. Imagine, again, we have this imaginary boss who comes every next day to you. He comes to you and he says, well, we've got a problem. This spot is too dark, and I need it to be illuminated just equally as any other place of the surface. He lives in two-dimensional world, and this is his problem. Sure, you could just grab some kind of lighter and, make sure that this part gets additional illumination, and, well, the problem would be solved for your boss. But actually, before doing that, if you not jump into the action straight away, and if you sit and think a little bit, you might get to abstract away from the two-dimensional world to three-dimensional world, and you would discover that there is actually something blocking the sun, and that's why we have this shade down here. So once you got to see the picture on the three-dimensional, one extra dimension level, then, well, you could just, I don't know, by some means remove that sphere from the three-dimensional world. That way you solve the problem of your boss. And there is a nice implication from there. By solving things one level ahead of abstraction, you tend to provide durable solutions. Again, let me illustrate. For the sake of example, maybe the sun has changed the angle, and now this shade, it has slightly moved away from its original spot. Because if you only patch the problem, if you were only eliminating this exact piece, your boss is going to come back to you and he say, well, guess what? We again have this problem. And you would again, I don't know, come up with some local illumination to get it solved. But actually, if you solved it, well, if you took this thing away on the three-dimensional level, then there is no way any change of external changes in the environment is going to reproduce the problem. And that's what I mean when you should seek to think of things on abstract level. All right. Another slide about divide and conquer strategy. As I said, human brain can only hold so many things at a time. In my imagination here, I don't know, in my brain I could hold, I don't know, maybe up to a dozen. If I start drawing things, maybe I can fit up to 20. I would definitely say my top is 50. And sometimes by having 50 objects is not enough. Well, some projects, some systems you're working on, they are too complex, and breaking them down up to 50 pieces is not enough. So there should be some way to tackle also that part. The way I suggest you to do about it is to introduce some kind of vertical hierarchy. So again, you might have the whole system. That system might have some, again, billing component, the user notification system, and that's fine. Well, that's already a more or less detailed picture of the system we're working on. In case if you're interested, you can kind of zoom in into the user notification system, and you would actually discover that there are some action happening in there too. For example, there could be a component, a subcomponent that sends email notification of certain content to certain email address. There could be another subcomponent that sends a text message to a certain phone number with a certain context. So that way, by introducing this hierarchical level of division, you manage to continue to recursively break things down until you really reach the level that satisfies your needs of well, dividing the code into components, while at the same time you keep, at any moment of time, you keep the amount of relations and objects to a number that is manageable and comfortable for your brain. Well, another hardly related slide to architecture, but anyway, I decided to include it. How do people go to the moon? I said and questioned myself how it actually happens. Well, my answer is up there. So first, you come up with certain of design. Okay, so we need a spaceship rocket, definitely, to get there. What do we need within that spaceship rocket? Maybe an engine, navigation system, external body for the spaceship. Okay, so then again, by divide and conquer, you recursively design each of those components. Again, engine could have had some kind of cooling system within it and so on. Then once you finish the design part, you actually proceed to the implementation. You go and build the factories, infrastructure that builds those components, and somewhere where you eventually assemble that whole piece, the whole spaceship, from the individual components. And then once you have that done, you just kick in, you plug in the factories, and they start producing parts, producing components, and that's how you go to the moon. Sounds logical, isn't it? What do you get from there? First of all, you get a bunch of reusable components. You might have needed this engine to go to the moon today, and that would be the end of the story. But 2 days after, you might be willing to travel to another planet. Chances are that engine is going to be just good enough to put it on some other kind of spaceship that's going to take you to another planet. Another thing that is really nice that you manage to certify, we call it to test in software, and to delegate, manage resources. For example, the guys who are responsible for doing engine, they have finished, they've produced their engine, but the guys who are working on the navigation system, they are not done yet. So, well, instead of letting these people do nothing and enjoy their life, you could have them retest and revalidate the engine they've produced. They might conduct the necessary tests and so on. And again, if you've leveraged well enough the vertical division of the things, you could test just the cooling system by itself, or the whole engine as a component. Or if that engine has something to do with the navigation system, if there is interface that connects them, you could test just the engine plus this spaceship body the navigation system without the other components. It was also really nice to manage and divide resources. If you had $1 million to execute this project and probably 1,000 people working on you, if you try to solve it horizontally, it's impossible. That's just too much of resources. So you say, all right, we have 3 subcomponents. Let's assign 30% of resources to the engine, another 30 to spaceship body, and yet another 30% to navigation system. So again, dividing vertically, you gain even more on this scale. And well, lastly, you get it on the mass production level. You were planning to go just once to the moon, but actually now you can travel wherever you like, and that's also a cool option to have. Well, now, yes, I'm going to connect all of this stuff to programming and software development. Apparently, well, I see some similarities. Apparently, step number 3, this one, that's computers who execute our code. So that's definitely not in my domain as a developer. But the first 2, the number 1, design and building the infrastructure, these 2 are my job description as a programmer. I am the one who's going to come up with layout of the components, and I'm the one who's going to then code those components, and so computer then can execute that code. And it is very logical to see these things on the case of the moon as, yeah, sure, we should have 3 steps. But things come down to software. Sometimes the step number 1 and step number 2 is not clearly distinct. And people, that's why I put the bottom line, well, when people go to spaceship, they don't go to the action straight away. They don't grab hammers and nails. They first think. And sometimes when we receive a task as developer, we actually tend to jump on it and, straightly code all of it. No, you should spend 55 minutes thinking about the problem, so then you take 5 minutes to solve it. So what would be traits, characteristics of successful architecture? Again, I wish I could have given some more specifics, but it is a very philosophical subject, architecture by itself, and then speaking philosophically about architecture is like philosophically speaking about philosophy, so don't expect much of specifics here. However, I say a code that is well done as far as architecture tends to look this way. If we stop at any place within the code, you should be able to logically explain from the following point of view. I am this kind of component. For example, I am a user notification system. I implement the following service. For example, I can notify a given user for a given event that might have happened to his account. And in order to fulfill that mission, the thing that I do, I actually depend upon some other components. I might depend on a component that sends emails, and I might also depend on a component that sends text messages on cell phones. And then if you look through the source code, it should really look like, all right, so we come in, here's a request from top, somebody invoked us. We received certain input arguments. We might slightly tackle them, I don't know, compare to something, multiply by something, and then we pass it on to one of our dependencies. We get it back from there. We slightly alter or analyze the output. We might do some if, else branching, so on. And then we pass it on to maybe another dependency. We receive it back. We slightly additionally process that thing, and we reply it on top as a result of our interface. So it should look like you're just pulling a bunch of strings, like you're not exactly doing things, but you're just using others kind of to do things for you, and just overseeing the process or just doing a few branches here and there. Also, I suggest you to make sure that critical gears business critical gears of your system are easily replaceable. That is, they are self-contained as some kind of components. Definitely your boss is going to enjoy that part when something happens, and yeah, if that part is not easily replaceable, well, that might be troubles. And if it is easily replaceable, then you can unplug this thing and plug something else on its place, and we're back in business. Architectures are also easy to explain verbally in human language, and then they might be a little more difficult to understand by just looking at the code. And why is that? I would say because, again, when we go to factory and we see some engine being assembled on the production line, well, you see the product, you see what, but you don't see why. Why is that engine using this kind of fuel? Why is it using that kind of cooling system? So this part of why, unless you put it in comments within your code, it stays out because the code is 2 dimensions and design is 3 dimensions. So there is just not enough explicit, verbosity in the code. And also the way business value looks when you code, there are actually 2 alternatives. The red line, this one, I say that's what it looks like when you don't when you don't use architecture. For example, you have a task. I have to dig a hole here. Well, it's going to take me 10 days to dig it. Guess what? I'm going to dig 10% of it a day. So I just, deliver my value 10% of the time, and that's it. However, if I use architecture, things might look more of this way, because at the beginning I do nothing. I just stare at the sky and I think I'm trying to analyze the problem abstractly. Somewhere closer to the middle, I might be coding individual components, but we're still not speaking about real business value delivered there. And then at the very end, it really explodes exponentially because I already had those bricks, those components, and I just then I connect them with wires, and everything all of a sudden starts to work the way it should. Some more tips about what you could do to improve your architecture. I suggest you again, if you recognize any kind of self-sufficient operation that you can explain with a sentence or 2 in human language, in English or Croatian, do wrap it up as a self-containing component. Could be just a function. It could be, a microservice in microservice architecture. Again, I don't care about the shape, but make sure that it is also isolated and self-contained. Use quite a few layers of vertical division on that's the slide about divide and conquer strategy. Because sometimes you might be normally you will be willing to get big components, to reuse big components, but sometimes those components, they are not flexible enough. So you always have an option of picking up some smaller components that might be slightly more mass to work with, might be a little more of code, but you definitely gain much more flexibility from there. And having at the same time options of using something big or something small, that's definitely better than just having one of the 2 options. Also, you might be tempted to stuff as much as you can into interfaces, but that's actually hurtful. I say, because if you put too much things onto interface, it feels buggled. It becomes more difficult to explain in one sentence what exactly that interface is about. So there are actually more chances of people going to use it wrong way, those interfaces. So that's why I say putting too much hurts the completeness of the interface. So again, it is really about art, about some kind of feeling. Is this enough of things, how many things I want to put on the interface, or it's not enough? Architecture is also very context dependent. Architecture by itself, it is not good or bad. However, it becomes so whenever you start to analyze it within some kind of context, within some kind of system. So if you have a best friend who says, well, this architecture is just awesome, we use it, we're very happy, sure, they might be happy in their case. And even if you're trying to do more or less the same domain, you're doing more or less business in the same subject, it doesn't automatically imply that the same architecture is going to be just as good for your use case. Always use critical thinking to analyze whether this architecture is truly successful and useful for your use case. And invest time into validating architectures on paper, because, well, how long does it take? Well, drawing things on the paper, some boxes, some arrows, and so on. Well, you could spend 1 hour doing these kind of drawings, and you might discover some kind of error. Something might not exactly fit into each other. Well, and luckily, it's just going to be 1 hour of time. However, if you haven't done that part and you jump straight onto coding, you're going to spend 5 hours, maybe 2 days of coding. When you're going to arrive to the spot where you're going to see that these things, they do not match. And by that time, you would have wasted actually, well, 5 hours or 2 days of your time. And that would be as much as I can say to you about architecture. And if you have any questions, I'm more than willing to answer them.
Thank you. Can you suggest any method of communication between components?
Between components?
Yes, parent-child or something like that.
Can you repeat the last part? I didn't.
Communication between parent-child components.
Yes. Well, at least I would say from my point of view, again, as I said, if we part from the idea that the shape of interface is not important, it's more of what it stands behind that. So for example, if there are functions, then if your interface takes the form of a function, then invoking functions, that's just the way to go. Or maybe if we are talking about some object-oriented things, then again, it would be, you would use actually object-oriented interfaces, maybe some inheritance. So I'm trying to say, again, communication between the components, it is going to be dictated by the shape of the interface. Well, I hope that answers or not.
Hello. My question is how to ensure not to over-engineer your layers, number of objects, and things like that.
Yes. Well, that's, I would say, exactly where the art thing goes. And I was asked these kind of questions when I was rehearsing this presentation to other people. The recipe I could have come up so far with is try to analyze any architecture that passes by you. For example, if you go to fix someone else's code and you see the architecture and it's now your turn to actually adjust that architecture, to deal with that architecture, try to analyze, is it really nice to adjust it? Is it flexible? Am I enjoying my time here? And if I'm not enjoying, what things could have been done better here? Or even often, if you come back to your own code, you might have coded something, half a year passed by, your boss comes in, you have to fix it. Again, you come back to your own architecture and you get a little bit of, now you're looking at it from a stranger position because you haven't been there for half a year. So again, whenever you're dealing with architectures, try not only to get things done, whatever that is, features, bug fixing, but also try to, again, from the 2 dimensions, try to come back to 3 dimensions and see, was this architecture useful and flexible enough to address whatever I had to do with it?
So it should be easily understandable, I guess. So.
Yes, and I would say, well, I always use the adjective of elegance. The good architectures, they look elegant. That's what I say about them. They're very simple. I'm very amazed by how much they solve with so little effort, and they're normally, speaking English, human language, they're very easy to understand.
Thank you.
Yes.
Any other questions?
Hi. One generic question. Have you used domain-driven design? What is your opinion about that?
Domain-driven?
Design.
I guess no, because I'm not sure what that is.
Ah, okay. Okay. Never
But
mind then.
Yes.
Okay, thank you.